First of all, as always, I try to compute this in triple integral. And the region T, the region T is defined by this condition, right? And in the integrand function, we have x. That means that the computation for this triple integral is no volume, is mass, maybe. If you suppose that the density function, is just x. When the density function is 1, entonces it's just the volume. So it's one possibility to apply the triple integral to compute the volume. Okay. Now, first of all, I need to do the graph in 3D. I know that the graph in 3D not always is 100% good because it's hard, even in Geogebra. Well, no. Some people they are super training in Geogebra apply another technique. Okay, I try to teach you, but not too much so far. About the surface and solid, no? But okay, first of all, identification. The first equation. What is that? What kind of surface it is? What kind? Help me. I need help. Parábola. Parábola es okay, pero parábola en 2D, pero en 3D. O sea, remember that at the beginning of this course, we are working in 3D. This is 3D picture, 3D view, and this is 2D view. In 2D view, we have different 2D view depending si you see from floor plan or lateral view. I agree with you. This is a parabola, okay? It's a parabola like that, no? Parabola like that. Okay, this is y equals x squared. But in 3D, how you see? Because my question was surface, not curve. What kind of surface it is? What kind? It's a plane? No. What plane? Plane si es a square. Plane is when it's linear. What happened, guy? Hey. The best student don't know anything about surface. Okay. Let me see the attendance. Rowing, Omar, David Restrepo, Heidi. Okay. Cylinder, of course, cylinder. It's cylinder. It's cylinder because one verb is missing, remember? Es cylinder. So es cylinder. Entonces es cylinder que en my opinion look like that. I don't know exactly. Let me try to do here another. Okay, this is a curve parallel to this. This is the parabola like that. Here, suppose que is similar. Okay. Let me try to erase this. I try to do my best. This is hard, I know. I understand this. Okay, this is a parabola like that. Okay, therefore, something like that. Okay, after I promise that we check it out in the Geogebra, but I need to do the roughly sketch in 3D and 2D. In 2D, in this case, I do, for example, this is y, sorry, C0. Suppose C0. Entonces this equation don't know depending on C, no? Okay. This is paraboloid cylindrical. Bueno, okay. Yeah. It's the name, yeah. Es cilindro, paraboloid cylindrical. Okay. Es paraboloid cylindrical. So remember, when the one verb is missing, in this case C is missing, this is cylinder, and this cylinder is alone the C axis, que es the verb que is missing. Okay? What about the second? The second equation, the second surface. What kind of surface? Plane. Okay, good. Plane. This is what's a plane. The clue is the plane guy. You know the degree of the variable is 1. This is cylinder. Cylinder. Paraboloid, whatever you want. The last name is not important. The first name is important. Cylinder. This plane is also missing one variable que is x. Therefore, this plane, for example, say I want to find the intercept on the axis. Suppose that I do in y equals 0. C is 1. C is 1. This point is here, 1. 1. And suppose C equals 0. Y is equal 1. C is 0, Y is 1. Okay, we have one intercept here, down. Okay, now, you connecting this and this. Let me use another color. No, the same color. 1, 1. Suppose this is 1. And this plane travel parallel to the x-axis, something like that. So you see this idea in the 2D, in which C is equals 0. Look. Well, I don't care in the first equation because the first equation do not depend on C, but on the second, is y equal 1. Y equal 1 and y equal 1 is a horizontal line. Y equal 1. Well, it's in both directions, but the problem is that we are working in the first octave. First octave means x positive, y positive, and c positive. So basically our region is that part in 2D. However, and to see a little bit complicated the solid. Well, we have a roof of this solid. In my opinion, it's a plane. It's a plane. It's a roof. Entonces we have one lateral wall que es de parábola, right? Entonces, entonces I suppose que the intersection, the connection between the cylinder parabolic and the plane, we have one line and that connecting this point and this point. It's no line, it's a curve. I suppose que es a curve. Because travel a little bit on the wall of the paraboloid, cylinder paraboloid. Entonces we have here one plane. This is flat. It's a roof of the solid. And we have another here, walk. Okay, it's not flat. It's a curvy a little bit, and it's my solid. Do you see or no? No necessary to do super sophisticated sketch. No necessary to set out the triple integral and compute the limit. No, it's not necessary super sophisticated 3D. Because the idea is, for example, see I make a decision to select the method of this Z symbol or X symbol or Y symbol. I don't know what is most convenient. You see what is the surface in the bottom and the surface in the top, or surface in the left or surface in the right, and also using 3D and 2D together, we set out my first and the triple integral, my first integral in 3D, and secondly, the double integral in 2D. Entonces, now we complete the triple integral. Bueno, okay. Entonces, do you see a little bit or no? O es confusing? The solid. Super confusing. Okay, let me try. Let me try Geogebra to see. See, we're doing the volume in the red region. Yeah, absolutely, Daniel, in the red region. No, it's volume, it's a mass. Remember, because the integrand function is no one. Entonces, no. Let me share the screen for the Geogebra to see in detail. Switching to screen. Okay, good. Okay, do you see the Geogebra? Do you see the Geogebra? Do you see or no? Good. Okay, first of all, we have the famous parabolic cylinder, no? Que es the red one. And you have a famous plane. Okay, let me remove the cylinder. Boom, no more cylinder. And this is the plane que represent like the roof, no, of this solid. And let me remove the plane to see the solid. And this is my solid. The thing I try to send this script in Geogebra, and you can see it here in surface. This is very complicated. Okay, this is beyond of the scope of this course, how you are doing the phases of this solid. Let me try to rotate to see the solid. Do you understand the solid? So the solid have for example, let me stop here. You see the purple color part is a plane. The red part is a piece of the parabolic cylinder, no? And the other hand, so and the other is just a plane. Okay, by the way, this is the plane. Let me see, the plane, one piece, no, of the plane x equals 0, que is belong to the YZ plane, no? Okay, so basically is, and also we have another phase, que is the bottom part, que is C equals 0. Do you see or no? It's clear now, super clear or no? Come on, I want to hear opinion. Clear. Okay. So always the problem that we are doing, okay, I encourage you, you try. I know it's hard to analyze my job in this script. Here in surface, look, in surface, we expand the surface. And this surface equation, I promise I want to explain this command surface in the chapter 4. But you take a look. This is no science fiction. It's possible to understand this. Okay, let's come back to the whiteboard. Whiteboard. Okay. Whiteboard. Okay. Suppose can make a decision using Z symbol. Z symbol, remember, is I have two surfaces, one above, one below, so top, bottom. Entonces now in the setup of the triple integral, integrand function is x. Suppose que I make a decision, integrate first with respect to z. So with respect to z is, let me use in blue color, is from this to this. So I go to the c. Okay, in this case, c is 0, it's obvious, right? To the c of the plane. Okay, the c of the plane is, look, the equation of the plane is y plus c equal 1, therefore c is equal 1 minus y. 1 minus y. I finish the first integral, in my opinion, is the most complicated part, because because it's the 3D. And the rest is the double integral. So that part is the double integral. Okay, you are doing this setup of this double integral in the 2D part. And the 2D part, you identification my region. By the way, this region I put in yellow color is this region. No? Okay. Now, well, this is classical. For example, I make a decision to integration in this direction, so parallel to the y, so it's dy, go from the parabola to the line. Y value, so y value from this to this. So it's from x squared, y equal, no, to y equal 1. And finally, we extending in both directions, bam, this dx from 0 to 1. Okay. This is the setup for the double integral. Consider the condition this C simple. Everyone understand the limit? How you find the limit? Come on. This is a crucial moment for me. This is the most important for me. You set out properly the triple integral. The triple integral you solve by hand or you put in all front alpha. No, remember the convention, the agreement was in the test on paper we solve everything by hand. And the test online, no. In the test online you solve it. Okay. Opinion. I want to hear opinion in this moment. Carlos Duque, Jocelyn, Robin, Omar, David, Heidi, Daniela, Fitby. Opinion, guys. Do you follow me or you are totally lost? Triple integral. Follow me. Okay. Entonces, as always, I want to skip this idea. The computation this by hand, or this is long. We spend maybe 5 minutes. Entonces, es 1/12 is the answer. Curiosity. Okay, you solving in only one way. You make a decision what is the way that you consider better. Suppose que another student solving using y simple. It's a curiosity. You don't need to solve it by 3 ways. Only one way is perfect. I want to illustrate, practice a little bit more, because the most complicated part we did before, que is the computation of the, do the sketch of the solid in 3D, do the sketch of the solid in 2D. Entonces es, suppose que I am doing in that direction. Look, parallel to the y direction. Entonces let me using another color. Suppose I am doing the integration. I make a decision, integration parallel to the y in that direction. Entonces this is my famous triple integral. This is x, but I am doing the integration first. Is y simple. Okay, so I can see in the green part, I go from the y of the parabola. Bueno, the y of the parabola is y equal x squared, no? It's that part. And the y of the plane, well, the equation of the plane, remember, was y plus z equal 1. Entonces, the y equal 1 minus c, no? So I go from x squared to y 1 minus c. This is the limit. When you integration and the direction of the green color, que is parallel to the y-axis, and this is, I make a decision to integrate first in that direction. It's possible. Ajá, entonces now, in order to complete the double integral, I am lost because the two dimension que I did before doesn't work. The two dimension que I using to do this is declare, for example, no C0, no, Y0. Y0. Y0 is, I don't know, is Y0 is, suppose that we have the equation that I have in my hand was y equal x squared, and we have the equation for the plane case y plus c equal 1, ¿no? Entonces I saw que y is common. Ajá, entonces I can write like that, x squared plus c equal 1. In other words, c is equal 1 minus x squared. Let me try to do the projection in 2D. But in this case, the axis is x-axis here and z-axis here. And this is the equation that I want to graphic. Bueno, esta parábola, the parabola open down, no? Because it's negative, right? Entonces here 1, 1. So basically, the thing that we try to do, well, let me finish. This is parabola open down, like that. It's a parabola open down. And by the way, this point is also 1, no? Because it's the when the z is 0, x is plus or minus 1, but I don't care this because I am working in the first octane only. Okay. So basically, this projection in 2D is the projections. Remember, see, I integration in the y direction. The projection is in the CX plane que look like that, in my opinion. Tuck. Look, it's the parabola like that. This is the thing that we are doing. This region is that region. Well, and this is double integral in this region is too easy. Suppose que you integration in this direction. Well, in this direction is dz. And dz go from the 0 to the c of this curve, que es this, is 1 minus x squared. And finally, dx, you extending this and this in both directions from 0 to 1, down. And this is another way to set up the same integral, and the answer, of course, is exactly the same. This is the beauty of the mathematics. Okay? Well, does a professor is possible doing in the x direction? Of course. Let me try to do my best. Suppose x simple, you integration. So that my triple integral, sorry, is x now integration dx first. Let me try to understand dz, go in this direction. In this direction, let me use in red color, why not? Also from this to this. Also now in the x direction, I go from 0 to the x value of the cylinder parabolic, this, pero x value. Entonces x is not already isolate, but I can't. I take out square root both sides, square root y equal x. I go from 0 to square root y. It's the x value when you integration in this direction. So I make a decision integration with respect to x, and the limit of this integral upper lower limit is x equals something, and x equals something. Okay, now, entonces are you projecting now in the in the ZY axis, no? In another plane. So I need to do something in the 2D picture. 2D picture is YZ. YZ. So YC. Well. YC. I suppose que es look. Suppose que es the plane. So like that. It's a line here. And by the way, the equation for this line is y 1 minus z, no? Que is the equation for the plane. Remember, in the plane, don't participate the x variable. Therefore, you see in the 2D picture exactly the same. So this is piece of cake. Okay, piece of cake. Suppose the integration can make a decision is in this direction. So I go from 0 to the z value of the z value. No, a ver si es bueno. I did that. Es from 0 to the y, que es to the y, to the que es let me see from 0 to entonces hay integration now and this z entonces es solve for here es c is equal 1 minus y. From 0 to 1 minus y. Okay, finally extending this in both directions from dy from 0 to 1. And we get exactly the same answer. Okay. My recommendation, I did by curiosity. Integration in 3 directions. However, no. In the real life, we are doing the integration only in 1 direction, no? And you get the result. So I try to illustrate that there are several ways, not always. In this elementary example, yes, it's possible. But the challenge is try to find the best way, the easy way. Can you solve it, for example, using only 1 triple integral, not 2 triple integral? Only one. So your integration in the z direction. So I prefer, in my opinion, I prefer always. Sometimes it's not possible, or it's more no convenience because your volume or your mass, whatever you want to find, is possible computing not only in 1 triple integral, but in 2. Those are no good. So I try to do in the easy way. 1 triple integral, well, when it's possible, of course. Another more complicated problem, no, it's possible using 2 triple integral. Okay, any question? This is a moment, okay, I want to interchange with you. Do you understand very well? So remember, guys, the technique I explained in the last class. In the triple integral, you manipulate in that way. You select the direction that you want to integrate. We have 3 possibilities: z, y, and x symbol. You determine the limit. The limit is easy because it's bounded by 2 surfaces. The surface that you consider in the top, the surface that you consider in the bottom. Okay, all the surface that you consider in the left, and the surface that you consider in the right, in the x direction or in the y direction. After that, we are doing the projection in 2D. So depending is the plane, no, like a perpendicular to the direction that you integrate in z and y and x. You are doing the sketch in 2D, and the sketch in 2D is too easy because the double integral exactly the same we are doing before. Any question? Any question? Everything clear? Let me see. Okay. Let me. By the way, do you see your grade in the blackboard? Do you see yes or no? Any discrepancy, let me know by email. Any discrepancy, let me know by email. Okay, I know that some students, I don't know why, some students no, all good. Some student forgot to send me, for you, claro. Some student forgot to send me the test on paper. Okay, entonces, as soon as possible, communicate with me. If you have some problem, you receive, you don't receive, you don't understand. But it's important that you check it, your grade in Blackboard, no? Because definitely this is the final grade, and that's it. Okay, let's move on again to the whiteboard. So I suppose that everyone understands this example 1. Let's move on to example 2. Example 2 is very, very, very interesting. Okay, example 2 is, let's see, suppose we have, well, in this case, volume, compute volume. Let's see volume, my function x comma y comma z is equal 1. Entonces es the solid bonded by 2 cylinder. Okay, x squared plus y squared. No, x squared plus c squared equal 9. Another cylinder gets y squared plus c squared equal 9 again. And this is bonded by the first one, octane. This is the solid T. Now I need to set out the triple integral and the T solid. 1 dV, because of the volume in this case, no mass. Okay? I try to do my best in the sketch of 3D, it's always complicated, very complicated. C, X, Y. I promise in the test you don't see complicated sketch, because this is another thing. I want you focus in the calculus part. And so there are problems in the books. It's science fiction. It's very, very complicated, and you spend a lot of time to understand the solid. In this case, no. In this case, we have 2 cylinders, right? Cylinder. This is cylinder. And this is another cylinder, yes or no? In this case, no parabolic. Daniel. In this case, no parabolic, sino es circular, right? Circular. And by the way, what is the radius of this cylinder? By the way, what is the radius 3? The radius 3. The radius 3 and both. It's a coincidence. However, the first cylinder, the first one, this is the first one, is along what? Along Y. Very well. So in my mind, in my opinion, suppose this guy is 3, this segment is 3, this segment is 3 also. We have here, and this is my first cylinder. This continue. I draw only the part belong to the first quadrant. See, it's complete. See, no specification this constraint, so it's completely cylinder, no? Okay. And what about the second? Well, the second one is similar. It's 3 again, the radius, however, it's along the x-axis, no? Because in my opinion, is something like that. It's a 3 also working here. Wow, what the hell? Well, my solid is this guy, look. This guy. This H. However, I can see here something like that in the intersection. I don't know exactly what is the equation of this. It's something like that. My solid. Make sense or no? It's roughly sketch. I am not sure. Now I'm working with the equation, no, to understand a little bit much better, right? I'm working with the equation. I create one script in Geogebra to see super clear. The 3D gets always complicated. I know it's very complicated. Okay, let me try. Open. Here you go. There you go. Okay, let me share the screen in order to show you the solid. Okay, there you go. Look at that. Here. Do you see Geogebra? Wow. Okay, look. I have two cylinders. The first one, for example, is the blue. The blue is along the X. Look, let me flash it. And the red is along the Y. Is the verb that is missing, no? In the equation. Now, the intersection of the cylinder, specifically in the first quadrant, wow, the base look like square. Okay, let me remove both. Boom. This is my solid. My solid is formed by this wall is the cylinder, that cylinder. This wall is another cylinder. Intention I put in similar color, no? Okay, now the for plan, let me see, this is X, Y axis. Remember, X is the red one, green is Y. This is square. And the, by the way, the size is 3 because the radius is 3. Okay, okay. Do you see or no? I need to compute the volume of this guy. I need to compute the volume of this guy. Do you see or no? Good. Okay, let's come back to the whiteboard. Because my goal is now try to set out the triplet integral can help me to compute the volume of this solid. Okay. The equation is, look. The equation is, I copy here. The equations, for example, I see in the equation, I see something important. Okay, the C is common in both equations. And see, you isolate C in both equations. Suppose C squared is equal to 9 minus X squared. And C squared in the second equation is 9 minus Y squared. And you put equal each other, so 9 minus X squared equal 9 minus Y squared. The 9 is canceled, the negative is canceled. And the square root both sides, X equal Y. Interpretation this. Suppose I make a decision, actually I am doing this order, to apply C simple. And your integration in this direction. Entonces now the projection and the plane perpendicular to this direction of the integration is this. Entonces now I am doing my graph in 2D. Let me try. My graph in 2D look like that, XY. Entonces you see que es square. 3 and 3 and 0. And this line is this line. So now, for example, well, when I set up the triplet integral, okay. My question is, how many triple integral you consider que es necessary to compute the volume of this? How many triple integral? Because my only one. Why? Why only one? Why only one? They are all equivalent. Okay, here no is equivalent. I don't like the word equivalent. I take advantage symmetry. This is always possible in engineer. Okay, so in the real life they are sometimes symmetric. Entonces now you set up only one part of the volume because I know that another I suppose que es the same. So you don't need to do this. You don't need to do this. Either way, you set out this or you set out that. Let me set out. Let me see. Well, okay. I don't care. Okay, suppose que I set up that part. This is my triple integral. The integrand function is 1 because volume. I integrate first dz. And dz go from 0 to the z value of this plane. By the way, let me see. This plane was x squared plus c squared equal 9, no? Because remember this circle, plane, not circle, cylinder. This cylinder is along the z. The z is missing variable. And this cylinder is x squared plus x squared, no, coño, is y squared, this one, y squared plus c squared equal 9. So I make a decision to do this, okay, or to do this. We have two possibilities. Let's do it in this order. In this order, my z go from 0 to the z when you isolate here. When you isolate here, the c is equal square root 9 minus y squared. Do you see that? Okay, good. Okay, now my region, or at least my region, when you integration in this direction, I suppose that my region, you let me know if I make a mistake or not, it's this part. Right? Under the consideration that the roof of the solid is, no, by the way, I make a mistake here. I make a mistake. This is wrong. This is wrong. Look, this is wrong. Okay. This part belong to this. This part belong to this. To say now c is equal to square root 9 minus s squared. Oh, much better, nice, no? Square root. Well, it's the same. Well, apparently it's the same. And that part, let me using another color for doing the double integral is that part. Okay. Okay. Entonces now to set out the double integral, bueno, as always, I like that way. I don't know why. Integration in this direction. In this direction is dy. Dy go from 0 to the y value of this case x. Look, this curve, the y equal x. I discovered that the intersection in between those cylinders is a line. And finally, when you extend it in this direction, is from 0 to 3. O sea, dx go from 0 to 3. Well, I know that the total volume is multiplication by 2, multiplication double, because I take advantage of the symmetry, no? So another possibility is set up this integral, que is very, very similar, very similar, very, very similar, but I consider it's better doing it that way. Now the rest is put in the calculator, put in Wolfram alpha. The answer is a little bit weird. It's 27 pi over 2 minus 80. It's the exact answer. Remember, in my lab, you need always the exact answer. When you put in the Wolfram alpha, when the calculator, and you don't get the exact answer, you get the approximation. It's because, okay, the interpretation is the antiderivative is impossible. And now the calculator apply numerical method to solve that. Okay? But in this case, no. In this case, it was 27 pi over 2 minus 18 is the exact answer, and this is the final answer. Any question? Any question? In the example 2. To say you a little bit understand the mechanism, the procedure, the strategy of the setup in Cartesian x, y, and z triple integral. Yes or no? Yes or no? Triple integral is similar. Victoria, I need to talk to you when the class is over, okay? Victoria, do you hear me? Victoria. Victoria Monforte. Okay. And Brandon also. Stay when the class is over. Brandon, do you hear me or no? Victoria. Wow. Well, okay. Okay, let's go to the exam. No example 3. Let me try. Brandon, when the class is over, stay. I want to talk to you. Okay? And Victoria also, both. In private. Or whatever. Okay, before to continue, another example, I want to explain another way to set out the triple integral. This is extremely important to make easy the problem. Okay, it's another kind of coordinate. So we have two kinds of coordinates. The first one is cylindrical. Cylindrical coordinate. Okay, cylindrical coordinate is super easy because cylindrical coordinate is like an extension of the polar, but in 3D. It's no big deal. Everyone understands very well cylindrical coordinate. Look, let me show you. It's the classical x, y, z. However, we have a point here, P. So we have, for example, what is the idea for the cylindrical? The cylindrical, the supposition is keep one Cartesian coordinate is exactly the same. For example, I want to call z, r, theta. So one option is one of these Cartesian x, y, or z stay the same. In this case, I select z, but not always. After I want to explain when you select x or y, I'm projecting the point onto the other plane that you don't select the coordinates. So si you select z, the other coordinate is missing is x and y. You project it onto the plane x and y, entonces you apply onto the xy the polar. This is my famous r, and this is theta. Entonces, sí es sí. Stay the same. But x, que I suppose que x is this segment, and y is this segment. Is the convention, is the like the polar, no? R cosine theta, and y is equal r sine theta. And stay the same que, for example, que r is equal square root x squared plus y squared, and theta, you know, is tangent inverse y over x. This is polar, pero polar in 3D. Is the only possibility? No. Another possibility is, look, suppose this possibility or this possibility. In this possibility, you consider the y. So we have a point and you project it here. Y. And in the plane xz, you apply polar. This is r, and this is theta. Always theta is measured from the x-axis or y-axis, never of the z-axis. But in this case, x is equal r cosine theta, y is equal r sine, y equal no, c, y, c is equal r sine theta. And the rest is, again, r is equal square root x squared plus c squared. Okay. What is most convenient doing in that way? Suppose we have one surface like that. We have another surface like that. So you integration in this direction first, and so this direction is parallel to the y, and you apply cylindrical, but supposition under the supposition, okay, y. So you're projecting this intersection in the CY place, and you apply directly here polar. Okay, depending the problem, no? The majority of the problem is different. It's like that. You have, for example, paraboloid, no? So you integration in this direction C, and you find the intersection to surface and projecting onto the XY. This is the 99%. However, we have different options. You suppose that y stay the same, y, or x is x. Que is in this direction. Suppose the point here, you're projecting. This is x, this is y. This is my point P, x is x. And in this case, the point here, you apply polar. This is theta. So theta is measured from x-axis frequently or y-axis, never z-axis. Entonces es cosine. And C is sine. And R is it's similar to this. And R is square root y squared plus c squared. This is R. Okay, entonces cilíndrica. What is the reason que es cilíndrica? What is the name? Well, the name is, look, is because you convert the classical three-dimension, you know, x, y, z, and for example, c, r, theta. So you suppose que c stay the same. Entonces, for example, c equal constant, again represent a plane. A plane parallel to the xy axis. C equal constant. R equal constant. Suppose que one equation que es R equal constant es a cylinder. Es a cylinder. Es a cylinder. Because, look. Suppose que es R equal constant es la que x squared plus y squared equal a number. 9, for example. Es a cylinder. That is the reason que the name is cylindrical. Coordinate. And theta equal constant. Theta equal constant. Bueno, theta equal constant es a plane. It's a plane again because suppose theta equal, I don't know, pi over 3, 60 degree. Entonces now this is theta equal something, 60 degree is something like that. It's a plane passing through this axis, and open in pi over 3. Okay, entonces es frequently plane and cylinder. That is the reason que es cylindrical. Entonces, my recommendation is try to using cylindrical coordinate when our solid contain cylinders, because it's super easy to find the equation of this. Also, paraboloid is good. And plane. So, the combination cylinder, paraboloid, plane is most convenient, always easy working using cylindrical coordinate. This is clear? This is easy because a cylindrical extension of the polar in 3D. So you keep one coordinate, the most popular is Z, and you're projecting onto the XY to the double integral, and the double integral and the XY you are doing in polar. Boom, end the story. Easy, elementary, but super useful. Because when you convert in polar, maybe the limit is no function, it's a number, and you can separate the triple integral and three integral so separately, and you compare separately, and you multiplication everything. This is cylindrical. Any question about cylindrical? Super confusing or super clear? Opinion using the chat. Victoria, are you there? You hear me or no? I suppose que you are not here. Okay. Okay, I understand. Entonces, everything clear, understandable or no? Ricardo, Gerardo. Clear. Okay. Okay, guys. Okay. Restrepo. Good, Restrepo. Thank you. Let me see now spherical. Another kind. I think an example. Yeah, of course. Yes. When you see example, you see more clear, Gerardo. But I want to discuss spherical first. Spherical coordinate. It's another kind of coordinate que is a little bit curvy, okay, because it's spherical. Spherical look like a ball. A spherical coordinate. Let me explain a spherical coordinate. A spherical coordinate is different. Look, guys, pay attention. This is a little bit weird. I know you are familiar to say you understand very well. But at the beginning, it's weird. Suppose that we have the classical three-axis. Suppose that we have a point, P. So instead of defining P like a normally X, Y, and Z, no. We are doing now a little bit like a polar, but we are polar. Look. We're connecting the origin to the point. And this segment is called rho. It's a radio vector, position vector, rho. Entonces we projecting here, for example, in the XY plane, and this guy is R. And this angle is theta, like a polar. But we have a new angle, is this angle, que phi. Es el Greek letter, phi. Okay, entonces en spherical, we convert for the classical XYZ to new coordinate que es rho, phi, and theta. Okay. Theta is angle, and theta can be vary from 0 to pi. Well, depending on the figure, no? The figure is completely, I don't know, sphere, cone. Si es hemisphere, well, maybe no, but it's okay, 0 to pi. Phi is important to understand. It's different. It's weird. The student don't understand very well phi, because phi 0 is exactly on the z-axis. Okay, see very in this direction, shun, 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 and ending in pi. And pi is completely here. This is the range of phi from 0 to pi. From 0 to pi. And rho, no, rho is no angle, it's a segment. Entonces rho vary from 0 to infinity. Okay, rho vary from 0 to infinity. Let me try to understand the equations, the formulas for the state relationship between rho, phi, theta, x, y, and z, x, y, and z, x, y, and z. This is y, this is x. Okay. So basically, we have one first. Okay, let me try to understand this. Suppose we have a R. Okay, R is this segment. Look. R. Wait a sec. Okay, this is R. This segment is R. This is a rho. Rho is bigger as a hypotenuse. And this is Z. Look, this triangle is this triangle. Look, rho. This is Z. This R, sorry, Z and rho. And this angle, this is Z-axis, Fe. 1. Therefore, this is R again, and this is Z. Entonces, using elementary trigonometric. A cosine is adjacent, the sine, the phi, and likewise R is equal to rho sine phi. That's it, no, because after we have another triangle, que es the classical triangle that you know, que is suppose this triangle in the xy plane. In the xy plane, we have the classical x, we have the classical y, and we have r. And this angle is theta, que is different to phi. Phi is another angle. This is theta. Let's obvio que, for example, x is equal r cosine phi, and y is equal r sine phi. But I know that r is rho sine phi. This is theta, sorry, theta. I confusing the name. Theta, phi. And x is equal, see you, for example, substitution r for rho sine phi. Entonces es rho sine phi cosine theta. And this is the formula, K connection, the new parameter in the spherical coordinate rho, phi, and theta, and x. And rho sine phi sine theta is y. And z, well, see, I got it, is this equation, is rho. Let me copy here. C is equal rho cosine phi. Es obvio that, for example, rho Rho square, apply Pythagoras. Rho is square root r square c square. But it's obvious also that r is square root x squared plus y squared. So you connected this equation and this equation, because r squared is x squared plus y squared. Es obvio que rho es equal to square root x squared plus y squared plus c squared. Wow, formula que connecting x, y, and z and rho. Okay, formula que connecting phi, theta, and x, phi, theta, and y, and rho and phi and c. This is the equation for the conversion in both directions, so Cartesian to spherical or spherical to Cartesian. What is the advantage to working with the spherical? Well. Suppose the equation of the sphere in Cartesian is, for example, x squared plus y squared plus c squared equal, I don't know, 4. It's a sphere with the center and the origin, and the radius 2. When you translate this to spherical coordinate, es la que dice rho equal to. Because I know, look at this equation. X squared plus y squared plus c squared is this upper part. Equal 4. Square root 4 is 2. O sea, es constant. O sea, this is a sphere. En spherical. Of the sphere. And the spherical is just rho. Suppose now a cone. A cone is, look, suppose phi equal pi over 4. It's a question of the cone. Wow, why? Well, the equation of the cone is suppose using the intuition. Look, suppose a cone like that. Like that. This suppose one example, no? Another maybe, I don't know. This is phi equal pi over 4. So this equation, phi equal pi over 4, represents a cone. Well, and theta equal a constant, pi over 3, again, it's a plane. Okay, entonces plane con sphere. Es the classical figure en spherical coordinate. Entonces, en the problem that involve, con sphere and plane is most convenient using spherical coordinate. Entonces, in my mind, look, the organization of the brain, my brain is, suppose the hypothetical case in what my solid is formed by just a plane. Entonces, most convenient x, y, and z. Suppose that my solid is formed by cylinder, plane, paraboloid. It's most convenient working with the cylindrical coordinate. Suppose that my solid is formed by a sphere, cone, plane. Entonces, most convenient using spherical coordinate. Okay. Let's go to the one example que include everything. Entonces, now it's important the selection of the coordinate we are using in one specific problem. Okay, in this example 3, we have, in this example 3, we have a mass, so I computed the triple integral. The integrand function is x dv, and the region of the solid T is formed by, look, x squared plus y squared equal 9, x squared plus y squared equal 4, and c is equal x plus y plus 5. And of course, no limitation. All right, let me see. Sí, es, and C is greater. No first quadrant, sino es. Okay, this is my solidity. Okay, let me try. Thinking about the surface que es forming my solid. Let me try to find in Geogebra. Okay, pero no, let's do it by hand. Es the exact side of the. Okay, there you go. I found. Okay, there you go. Boom, boom, boom. Good. Okay, let me try to do my best in 3 dimensions, que it's always hard. Suppose 3x. I have no idea. Say using a cylindrical or Cartesians or spherical. In this moment, I have no idea. First of all, identification. The surface que participate in the game. What is that? The first one. Name, cylinder. The radio is 3, no? Cylinder. Circular cylinder, radio 3. Entonces, in my opinion, look like that. Suppose this is 3, this is cylinder. Cylinder. Along C-axis. Along C-axis because the verb is missing. Super. And the second is exactly the same, no? A cylinder, pero radio 2, no? And the same direction, the same orientation. Entonces 2. Another cylinder. This is standing forever in both directions. No in both directions, because the restriction is que C is 0. That part is invisible. No, the bottom part, only the top part. And the roof of this, I suppose, is bounded by the plane. And the plane, this is the plane, no? It's the plane. And this plane, I have no idea. Let me see. Okay, suppose que X is 0 and Y is 0. Entonces C es 5. Okay, entonces something like that. Let me extend a little bit this axis. F5. Suppose que es 5. Okay, F5. Suppose now, X 0 and Y, C 0. The solve for Y, entonces 0 is equal to 0, es negative. O sea, Y is equal to -5. Okay, suppose, okay, C0, X0, solve for Y, -5. Okay, -5, I suppose, que es like that. Same distance, pero es -5 en Y-axis, no? Now, like Y, suppose Y0, C0, X is equal to -5. And -5 here. Entonces my plane look like that. And entonces somehow, I'm not sure, the cylinder is bounded by the roof, que es this plane. So basically, what is the idea? The idea is you have 2 cylinders, one radio 3, one radio 2, and we have one plane that cut up the cylinders in the top part. Well, This is complicated to see. However, I bring the Geogebra to illustrate the idea. Look, let me show you. Let me try to show you. Okay, 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 okay. Something like that. Do you see Geogebra? We have two cylinders. Yes. We have two cylinders, guys. Red and green. Boom. Look at that. Boom. Boom. Two cylinders. Boom. Boom. And we have a plane. Okay, this plane. Wow. And the okay muffler. It's a muffler. Okay, and the solid is obvious. Okay, is formed by two cylinders, the inner and the outer cylinder, and cut off the top by the plane. To see this and the by hand is a little bit complicated. So today, don't worry, I send this script and you analyze at home by yourself. Okay, as you understand a little bit, let me try to set up the integral. Entonces now, selection, what kind of coordinate we are using. I suppose que es obvio que we use cylindrical, ¿no? Because it's cylinder, entonces cylindrical. And the projection, o sea, the Cartesian que you keep is Z. C equals Z. C equals Z. C equals Z. Entonces, the thing I try to explain is que not necessarily you need to understand accurate 100% the solid. We're doing roughly sketch 3D. And you automatically you infer que we use cylindrical. It's obvious, two cylinders, one plane, cylindrical, it's obvious. Spherical, no. Spherical is sphere, es sphere, con. Entonces, Cartesian maybe. Pero no countable. So it's, okay, immediately, si you make a decision that you keep C equals Z, and you project it onto the XY plane, look at that XY plane. This is a two-dimension picture. You see the idea is super clear. The idea is two circles. One circle with the radius 3, and one circle with the radius 2, and the center is in the origin. And at least this is my region, or at least the projection in 2D. And to do this using polar is super easy. So my solid, I don't know exactly, but it look like that. I know. Sorry, carajo. Okay. One more. Share the screen. Boom. 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 Do you see now? Okay. No, the thing I try to explain is, suppose that you have no clear idea for the solid. It's confusing. I try to do my best. However, when I make a decision to apply cylindrical coordinate, you keep one variable stay the same, is Z. In that case, C is Z. And when you project the C is Z, when you project it in the perpendicular plane, que es XY, the solid you see like that, like a ring, like a one ring que contains two circles. The inner circle is 2, the outer circle is 3. And this is super easy to set out in polar. This is how you set out the triple integral. Well, the integral function is x. And you write no x because you're switching everything to the Remember, we're switching x, y, z to c r theta. Well, okay, but I know x is equal r cosine theta. So the integrand function, you need to express it using the proper coordinate, so the variable que participate in the game, que es c, r, and theta. Entonces my x is r cosine theta. dv. And dv is dz. Entonces now in polar is r dr d theta. O sea, the Jacobian, I forgot to say that. The Jacobian in cylindrical is exactly the same the Jacobian in polar. The Jacobian in spherical, I forgot to say, but in your moment I explain that. Okay, entonces I integrate with respect to c, and c go from 0, que es this, c equals 0, to the c of the plane, que the c of the plane is this. Entonces I copy c of the plane, que es x plus y plus 5, pero no like that, because this variable now disappear. No x, no y, no c, yes, but entonces now you change. The limit is r cosine theta, que es x, plus r sine theta, que es y, plus 5. And this is my c value, que es this. Okay? When I finished the complicated part, que was the first integral of the triple integral, this is now piece of cake, because now is the double integral in that region to the and we use polar, of course, and the radio go from 2 to 3. And theta go from 0 to pi, because there's the total ring. It's the total ring. See, we have, for example, 1/4 of the ring, no. But in this case, total ring. And this is my triple integral que allow me compute the mass of this solid. Put in a calculator, the answer is 65 over 4 pi. Boom. Boom. Any question? Any question? Oof, what the hell is that? Any question? Confusing, clear? Okay, let me see. Clear. Okay, good. I like that. Okay. Okay, I bring another example in which we're using example 4, suppose it's the last one, and let me try to erase the board. Example 4, no? Yeah. Example 4. Let's compute the triple integral again, but in this case I have volume. Compute the volume, use the triple integral, volume. Automatically, as you see here, volume is because the integral function is 1. So triple integral and the solid T 1 dV. And the solid T is formed by the following curve. Look. Okay, the first one is C equal x squared plus y squared. The second is C equal 4 minus x squared plus y squared. Minus, sorry, minus, both minus. And that's it. Okay, is the the solid formed by two surfaces. It's easy. C is isolating both. Entonces es obvio que we use a C simple, no? Or no C simple because, okay, what kind of surface? Identification of this. Okay, a sketch in 3D. What is the name, first name, and last name of the first surface? And how it look like? Elliptical. Actually, it's circular. Circular paraboloid. Paraboloid is circular? Yes, you're right. Paraboloid is circular. Okay, and the paraboloid, both are paraboloid or only one? Okay, the first is paraboloid. Like that. Open up. Because it's positive, no? The parabola open up. In this case, also paraboloid. Yes, but open down. We have one vertex of the paraboloid and 4. Actually, we have paraboloid. Suppose here a 4 and this paraboloid open down. Entonces, in one specific point, I have no idea, both paraboloid intersect. So this is this equation, this surface, and this is the second. No, and this is the second case open up. Do you see that? Wow, it's easy. My opinion, no? It's easy. Do you see or no? Opinion. No? Come on, guy. Opinion. Do you see the two paraboloid or no? Yes, I see. Okay, look now, Gerardo. Suppose now, Gerardo, I want to illustrate this idea in Geogebra. Sure, time is over. Almost over. Okay. Let me try to do my best now. We come back in this problem next class. Okay, look. Share screen. Geogebra. Switching Geogebra. There you go. Boom. Do you see Geogebra? Wow, amazing. I like that. Look, one paraboloid open up. Look, it's open. This is paraboloid. This paraboloid open down. This paraboloid. Okay. And this is the intersection. Okay. So it's easy to understand. Well, at least for me, it's easy to understand. Okay, you can integration using cylindrical. Okay, Ricardo, sketching low. Wow. Okay, I try to do my best, guy, to prepare this lecture for you, no? I suppose you appreciate that. Now, okay, do you like, no? Don't worry, I sent to you this script, and you using your imagination to understand how you create this surface. I anticipate a little bit. Okay, you don't know exactly. Do you see whiteboard now or no? Or not yet? Whiteboard now? No, not yet. Okay. Okay. Now whiteboard? Okay. Entonces, bueno, no, I don't finish this, pero es obvio que the first integral and the triple integral, yo integration, for example, like that, and C. And you suppose C equals C. And now, what is the problem now? You're projecting. So your intersection, both surface. I try to find that curve, okay, the intersection to surface, and you projecting this in the XY plane, and you apply here polar, I suppose. Okay, we continue this problem and more complicated problem Wednesday. Please check it out. You're great. En Blackboard, any discrepancy. I know que